So today we're going to talk about counting. And this is one of the central problems in this course, and it comes up all the time. So basically, we want to do something, and the question is, how many different ways do we have to do it? And these are the counting problems that we're going to focus on. So we're going to see many different counting problems, but I'm going to start with some very easy techniques, and then I'm going to build from them and get better and better techniques as we go on. Okay, so here's the first one. This is called the principle of addition, or just PA, or also known as casework principle. So imagine this. Imagine that I have two cities. Let's say this is A and this is B. And let's say that I want to go from A to B. Okay. And let's say that there are two roads from A to B. Okay. And so there are two ways to go by car, let's say. And then let's say there is one way to fly from A to B. And then let's say that A and B are next to the sea. So there are also two ways to take the ferry from A to B. Okay, so I have this. What is the total number of ways that I can go from A to B? I told you this is going to be easy. It's just the sum of the number of different ways that I had here. So it's just 1 plus 2 plus 2, which is 5. Right? So in general, the principle of addition is what we use for casework. So let's say that I want to do something, or I want to count the number of elements in subsets. And then I'm taking this set and I'm dividing it into several smaller sets. Then the number of elements in my big set is just the sum of the number of elements in the smaller sets. So here, if I'm talking about the number of ways of doing something, I want to talk about the number of ways of going from A to B. I'm just doing the casework. I'm saying that, well, either I go by land, or I fly, or I go by sea. And then I have two ways of going by land, one way of flying, and two ways of going by sea. So I have 5 ways of. Okay. So this is very easy. We sometimes also call it casework principle, because this is what we use when we're doing casework. So dividing something into several different cases. Now, the other one, which is a little bit more interesting, is the principle of multiplication. So we use this one when we have several different steps, let's say, and every step is completely independent of the previous step. So imagine something like this. Again, I have two cities, A and B. I want to go from A to B. But in order to go from A to B, I have to go through some intermediate cities, let's say C and D. And let's say that I have two ways of going from A to C. I have 3 ways of going from C to D. And I have, again, 2 ways of going from D to B. Okay. Now the question is, how many different ways do I have to go from A to B? Well, infinitely many, right? Because I can start from A, go to C, go to D, go back to C. So I have infinitely many ways of going from A to B, but how many ways do I have to go from A to B if I always move to the right, if I can never move to the left? So in this case, you see that I have 2 ways of going from A to C, and then I have 3 ways of going from C to D, and then I have 2 ways of going from D to B. And I can take any combination of these ways. So this independence aspect is really important. So no matter which way I chose to go from A to C, I can choose any of the ways for going from C to D, and so on. So my total number of ways is just 2 times 3 times 2. This is the principle of multiplication. So we want to solve some problems starting with this very basic principle. So I have 2 ways of dividing my problem. I have a problem, I want to count how many ways can I do something, and maybe I can do a casework, and I know that whenever I do casework, I have to use addition, or maybe I can divide my problem into several independent steps. And when I say independent, I just mean that the number of ways is independent. So no matter which path I took from A to C, I have 3 different choices at C. Now, it's fine if these choices actually depend on the previous choice, as long as their number does not depend on the previous choice. Okay, so imagine if I said that from C to D, I actually have 6 ways. So these are all the ways from C to D. And from A to C, I have something like this. I have 2 ways. One of them is blue, one of them is red. And suppose that I had this rule that if I took the blue path from A to C, then I have to take the blue from C to D. And if I took the red from A to C, I have to take the red from C to D. I can still use the principle of multiplication because no matter which choice I choose in my first stage, in the second stage, I have 3 choices. So I don't care that the choices themselves are different. I only care about the number of choices. Okay. So based on this, let's try to solve some relatively easy but very central problems. So the first problem I want to solve is the problem of counting permutations. Okay. So let's say I have the numbers from 1 to n. And by the way, this is the notation that I use. I use bracket n to show the numbers 1, 2, 3 to n. Okay. So let's say I have all of these numbers, and a permutation of these numbers is just one ordering of the numbers. So a sequence of length n in which each of these numbers appears exactly once. So for example, let's say I want to look at the permutations of 1, 2, 3. Okay, if I have the numbers 1, 2, and 3, what are the different permutations that I can have? Well, I can have 1, 2, 3. I can have 1, 3, 2. I can have 2, 1, 3. I can have 2, 3, 1. I can have 3, 1, 2. And I can have 3, 2, 1. So hopefully there are 6 permutations. 1, 2, 3, 6. Yes. So I didn't miss it. So there are 6 ways of writing the numbers 1, 2, and 3 in some order. And we call this permutations. So there are 6 permutations of 1, 2, and 3. Okay. Now, I want to count how many permutations I have if I have n numbers. So another way of thinking about this is that I have n people. I want to create a queue of this n people. How many different queues can I make? Okay. So here's the thing. Suppose I show this number by x sub n. So let's say x sub n is the number of permutations of the numbers from 1 to n. What do I know about x1? If I have just one person, how many different ways do I have for putting them in a queue? Just one, right? So x1 is 1. Now, suppose that I want to find xn. Okay. And this is the first example of a recursive definition in this course. So let's say that I want to put n different people in a queue. I want to divide it into 2 parts. I want to say that, well, I want to use the principle of multiplication. So let's use this, but let's also get inspiration from induction. So I have n people. Let's first ask n minus 1 of them to stand in a queue. And I know how many different ways I have for that. That's just x n minus 1, right? And now let's say that I have these n minus 1 people in a queue. Okay. Now I have person number n, and I have to insert that person somewhere in this queue. But how many different places do I have? Where can I insert this last person? I can insert them at the beginning here, or between the first and the second person, or between the second and the third person, so on. Or I can insert them at the very end. So I have n different places for putting the last person. Okay. So my total number of ways is going to be xn minus 1 times n. Because I wanted to create a queue of n people, I divided this into 2 steps. The first step was that I create a queue of n minus 1 people, and I know that the number of ways of doing that is just xn minus 1. And then the next step was that I'm going to insert the last person in. And no matter how I did the first step, I can do the second step in n different ways. So my total solution, the total number of ways is going to be xn minus 1 times n. Now, of course, if you just follow this definition, you see that x1 is 1, x2 is 1 times 2, x3 is 1 times 2 times 3, and so on, right? So generally speaking, xn is going to be the product of all the numbers from 1 to n. Okay, and we give this a name. We show this by n factorial. So this is n factorial. It's not an exclamation mark, it's a factorial. And also, whenever you're writing your solutions, please don't use exclamation marks at the end of your sentences, because I don't know if it's a factorial. Okay, so this is n factorial. And generally speaking, I can now define n factorial in 2 different ways. I can say, whenever I say n factorial, I just mean the product of the numbers from 1 to n. Or I can say that I define n factorial as the number of permutations of n numbers. These 2 are the same. Okay. Fun question. What is 0 factorial? Yes, 0 factorial is 1. It is a convention, but I have a better reason for it. Why is 0 factorial equal to 1? We just talked about this definition of factorial, which is not based on just multiplying numbers. It's actually based on saying I have n people and I want to put them in a queue. So imagine that I have 0 people. And yes, I want to put 0 people in a queue. How many different queues can I have? 1, the empty queue. Right? So 0 factorial is 1. Okay, great. So we saw this simple problem where I had n people and I wanted to put them in a queue, and we saw that the number of ways is n factorial. But let's just count the same thing in a different way. So another way of looking at this, if I don't want to have a recursive or induction-based definition, is this. I want to create a queue of n people, and let's say that I have n empty places. So place 1, place 2, place 3, so on to place number n. And basically, I have to put one of my people in each of these places. Right. So how many different choices do I have for the first place? I can put any of the n people there. So I have n choices for this one. Now, how many choices do I have for the second place? Well, whoever went into the first place cannot also be put into the second place. So I have n minus 1 choices. Okay. And I can continue this. How many choices do I have for the third place? N minus 2. And so on, until I ask how many choices do I have for the last place, and it's just 1. And now I can just use the multiplication principle, and I can say that the total number of ways is n times n minus 1 times n minus 2 all the way to 1, which is exactly n factorial. Now, again, here the important point is that the number of ways I had in each step was independent of the choices that I made in the previous step. Okay. So no matter what choice I made for my first step, I had n minus 1 choices for the second step. The choices themselves are not independent, because remember, I'm saying in the second place, I cannot put the person that I put in the first place. So actually, the choices that I have here are dependent on what choice I made at the beginning, but the number is independent. And because the number of choices is independent, I can use the multiplication principle. I can say, I have n times n minus 1 times n minus 2, so on, which is just n factorial different ways. Okay, so I could just do it like this, or I could, instead of dividing it into n steps, divide it into 2 steps, basically. Okay. So this is permutations, but now we can ask something a little bit more interesting. So imagine that I have the same n people, but I don't want to put all of them in a queue. I want to only take some of them and put them in a queue. So let's say that I want to form a queue of length r. Okay. So how many queues of length r can we form from n people? So now I have n people. I want to keep only r of them, and I want to discard n minus r of them, and then I want to put this r people into a queue. And the question is, how many different ways do I have to do that? Okay, now I can try something similar to here, and let's see what I get. So I'm going to show this number by P of nr, or sometimes people write it like this, P of nr. So the number of permutations of r items from n items, or the number of queues of r people from n. Okay. So I can look at the second solution that I had before, and I can just do something very similar. I can say, well, I want a queue of length r. So let's say that I have r different places. So I have place number 1, place number 2, 3, so on, to place r minus 1 and place r. Okay. And now I have to fill out these places again, just as before. So how many choices do I have for my first place? I have to choose one of the n people to go into the first place. So I have n choices. Now, no matter who I chose for the first place, I cannot put the same person in the second place. So I have n minus 1 choices for the second place. And you see that the same argument just continues. I can have n minus 2 choices for the next one. How many choices can I have for the r's place? Yes. Yeah. So I just multiply all of these numbers. So basically P of nr is going to be n times n minus 1 times n minus 2, so on, to n minus r plus 1. Now, do I have an easier way of writing this? Well, yes. Look, this is just the multiplication of all the numbers, the product of all the numbers from n to n minus r plus 1. If it went all the way down to 1, I could just say it's n factorial, but it's not going all the way down to 1. But let's just do it. Let's make sure that I go all the way down to 1. So let's multiply this by n minus r, n minus r minus 1, so on, all the way to 1. And let's divide it by the same thing. Okay. So now in the numerator, I have the product of all the numbers from n to 1. So it's just n factorial. And down here, I have the product of all the numbers from n minus r to 1. So this is just going to be n minus r factorial. Okay. So we got a very simple formula for this. P of nr, the number of permutations of r items from n items, is just n factorial over n minus r. But are there other ways of getting the same result? So we asked this question over and over again in this course, and this is actually what we call double counting or sometimes dual counting. Basically, the idea is that I want to count the same thing in different ways, and I might get different formulas for it, but since I'm counting the same thing, I can say that they're all equal, right? So let's try to do this in a different way. So here's the thing. Suppose that instead of having R places, I had all of my N places, right? So this would take me back to the previous problem where I just had N people and I wanted to create a queue of them. And I know that I can do that in N factorial ways. So here's my solution for creating a queue of length R. I say first create a queue of length N, and then just keep the first R people. Remove everyone who's after index R. Okay, so for example, if I'm doing P of, let's say 6, 4. So I'm first going to create a queue of length 6. So let's say 6, 5, 4, 2, 1, 3. Okay. And then I'm going to say, I'm only keeping the first 4 people. I'm going to remove the last 2 people. Okay. Great. So I know that the number of ways of creating a queue of 6 people is just 6 factorial, right? But the problem is that now I have counted some solutions several times. So for example, look at 6542, right? I have counted it when I was looking at 654213, but I have also counted it when I was looking at 644231, right? So basically, every time that I was removing some tail of my queue, I'm getting this head part of the queue, but maybe I'm getting it several times, and maybe I'm counting it several times. Now, the interesting point is that no matter what my head part is, I'm counting it the same number of times, right? So in this case, I have 4 elements in the head part, the part that I want to keep. And so I'm going to have 2 elements in this tail part, the part that I'm removing, right? So how many different tails can I have? I can have 2 factorial, or basically 2 different tails, right? So if I look at each one of these heads, I know that I have counted it exactly 2 factorial times. So I can just count everything and then divide by 2 factorial. So it's 6 factorial over 2 factorial. Now, in general, it's the same idea. If I want to find P of NR, I can say first, just create any queue of length n. And I know that I can do that in n factorial ways, right? And then I'm going to say only keep the first R people and remove the last n minus R people, right? But now the problem is that for every group of R people, for every permutation of R people that I'm keeping, I'm actually counting it n minus R factorial ways, right? So I just have to divide this by n minus R factorial, which is, again, exactly the same formula that we had here. Okay, so we could get this by an algebraic manipulation, or we could get it by just being a little bit more careful about how many times we are counting every solution. Okay. Now, here's the thing. When we're talking about permutations, we're talking about distinct items. So I was saying I have permutations of the numbers from 1 to n. And of course, these numbers are all different, right? And also, when I was talking about humans, I assume that you're all unique individuals, so all the humans are different, right? But what happens if some of my items are not different? So let's ask a question like this. So first, let's do an example of the different one. So let's say I ask you how many permutations does each of the following words have? So suppose that I have a word and I'm just asking in how many different ways can I order the letters in this word? How many different words can I create using this word? And they don't have to be meaningful words. So let's start with our most beloved word. Okay. So how many different permutations we have here? 5 factorial. Yeah, this is very easy because all the 5 letters are actually different. And since the 5 letters are different, I can just imagine that I'm assigning a number to each of the letters, and I have the numbers from 1 to 5. I'm just asking how many permutations are there of the numbers from 1 to 5, and it's 5 to 12. Okay. But now, let's take some other word. Let's take this one. How many permutations do I have here? So you see, the problem here is that some letters are appearing more than once. So if I look at the letter A, it's appearing 1, 2, 3, 4, 5 times. Right. And these 5 different A's are not really different. They're the same for us. Right. So if I were to just consider them to be different, then I would get more answers than the case when they're not different. Okay. Now, this is kind of a long word, so let's just do something simpler. Let's do AABB. This is much simpler. So if I consider these 4 letters to all be different, then I would have 4 factorial different ways. But that's not really correct, right? Because if I consider them to be different, it's like assigning a different number to each one of them. So let's say this is 1, this is 2, this is 3, this is 4. And then I'm counting all the permutations of 1, 2, 3, 4. Right. So one of those permutations is, of course, 1, 2, 3, 4. But another permutation would be this one, 2, 1, 4, 3. Right. So when I'm counting 4 factorial, I'm counting these 2 permutations as different permutations. But if I go back to my letters, my letter 1 was A, my letter 2 was A, 3 was B, and 4 was B. 2 was A, 1 was A, 4 was B, and 3 was B. And I see that I actually have the same word. So I cannot say that I have 4 factorial different permutations here, because of course I don't, because I'm counting some permutations more than once. So that's a problem. Now, how can I solve this problem? Well, I can use a technique like the last technique that I used here. I'm just going to assume that the letters are different, and this will count every solution more than once. But as long as every solution is counted the same number of times, I can just divide by the number of times that I have counted every solution. So let's say that for now, I just imagine that these A's and B's are different. So I imagine that I have A1, A2, B1, and B2, and these are different letters. Okay. So I will have 4 factorial different permutations of these 4 letters. Okay. But in reality, my A's are not different. So I could take any of my solutions and I could just swap the A's, and I would get the same solution. And the same thing for the B's. My B's are not different, so I could take any solution, swap the B's. So basically, from every solution, I'm getting 4 different ways, right, of swapping the A's or swapping the B's. And it would give me still the same solution. So in other words, I'm counting every solution 4 times. So the total number of solutions is 4 factorial divided by 4. Okay. Now, I can do the same thing here. Suppose that all of these letters are different. So this is letter 1, A1, A2, A3. Oh, I forgot one of these. Okay, A3, A4, A5. I have B1 here and B2 here. R, I have R1 and R2. C, there is only 1. D is only 1. Okay. So first of all, I assume that these letters are different. So I assume that A1, A2, A3, A4, A5 are all different. And so on for the B's and R's and so on. So how many letters do I have overall? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I will have 11 factorial ways of creating a permutation of all of my letters. But now I can say that in each of these permutations, I can take all the A's and I can apply any permutation that I want, but it will not change the answer. So I've counted every answer 5 factorial different times on account of the permutations that I could apply to the A's, right? But that's not the only thing. I can also talk about the B's. So I have 2 B's. I have 2 factorial different ways of applying permutations to the B's. I have 2 R's. So I have 2 factorial different ways of that as well. Those were the only letters that were repeated, right? Yeah, so my answer is actually this. It's 11 factorial over 5 factorial, 2 factorial, 2. Okay. So you see, this technique comes in very handy. I just take items that are actually the same. I imagine that they're different. I count the number of ways, and now I say, okay, I've counted everything, let's say 5 factorial times, because I had 5 A's and there were 5 factorial ways of ordering the A's. Okay. Now, in general, let's say that I have a bunch of letters. So let's say that I have K1 letters of type 1. I have K2 letters of type 2, so on to, let's say, KT letters of type T. And I have a word that has these letters. I want to see how many different permutations I have. Again, I'm just extending the previous idea. First, I assume that all of my letters are different. So I have K1 plus K2, so on to KT letters. And the number of permutations would just be the number of letters factorial. And then I say, well, on account of type 1 letters, I've counted every solution K1 factorial ways, because I can take any solution and I can change the letters of type 1, change the order in K1 factorial ways, and I will still get the same solution. So I have to divide this by K1 factorial. And then for the same reason, I have to also divide it by K2 factorial, so on to KT factorial. Okay. Or if we want to write it a little bit nicer, it would be sum of Ki, I from 1 to T, the whole thing factorial, over the product of I from 1 to T of Ki factorial. We actually also proved something in number theory. I mean, it's a very simple theorem now. But here's the thing. What was I doing here? I was counting the number of ways of doing something. I was counting the number of ways of ordering the letters in a particular word. So the number of ways to do something would always be a natural number, right? So this means that this thing is a natural number. So it means that the numerator is actually a multiple of the denominator. So this is a technique that we will use as well. So I could just tell you without any kind of other side problem that prove to me that this number is a multiple of this number. And one way of proving it would be to just define some sort of counting problem and say, well, the answer of the counting problem is this fraction. And the answer of the counting problem has to be a natural number. Okay. By the way, the worst experience I have from this discrete mathematics classes is that once I asked the student to count the number of ways of doing something, and they came back with 9.5. So if you do something like that, I will fail you in this course. So it has to be an integer. Okay. Great. So let's now use the same techniques to solve some other classical problems. So here's a problem that we have already solved using induction, but let's now solve it like this. Let's say, suppose n is a set of n elements, or just let's take the set of all the numbers from 1 to n. I want to see how many subsets it has, and I claim that it has 2 to the power of n subsets. Now, we've seen an inductive proof of this before, but let's find a different proof. So let's say that I have all of my numbers, 1, 2, 3, all the way to n. Since I'm a computer scientist, I'm going to use 0 to mean false or not included, and I'm going to use 1 to mean true or included. So if I'm given any subset, I can write a sequence of zeros and ones, which basically tells me whether the first number 1 is in my subset or not. So maybe 1 is not in my subset, maybe 2 is in my subset, maybe 3 is not in my subset, and so on, and maybe n is not in my subset. Okay. So what I'm doing here is that I'm finding a one-to-one correspondence between the subsets and the sequences of zeros and ones. So if I give you a subset of the numbers from 1 to n, you can translate it to exactly one sequence of zeros and ones. And if I give you a sequence of zeros and ones of length n, you can translate it to exactly one subset. So this shows that the number of subsets is equal to the number of sequences of length n of 0 and 1. Right? So as a very simple example, let's say my n is 2. So my set is just 1 and 2. Now, what are the sequences that I can have? I can have 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So 0, 0 corresponds to the case where I'm not taking any of these two elements into my subset. So this is the empty set. 0, 1 corresponds to the case where I'm only taking 2. This one corresponds to the case where I'm only taking 1. And this corresponds to the case where I'm taking both. And you can see that here I have all the subsets of the set 1, 2. And here I have all the sequences of zeros and ones of next 2. Okay. And this holds, of course, for every n. Now, so if I want to count the number of subsets of a set of size n, all I have to do is to count the number of sequences of zeros and ones of length n. But that's a very easy thing to count because now we have the multiplication principle. So again, I want to create a sequence of length n. So I have n places, and in each one of these places, I have to write either 0 or 1. But they also don't depend on each other at all. So in the first place, I have two choices. I can either write 0 or 1. Now, independent of what I wrote here, in the second place, I have two choices. I can write 0 or 1, and so on. So I have two choices for every step. So the total number of choices is just the multiplication of all of these, which is 2 to the power. So any set of size n has exactly 2 to the power of n subsets. Okay. But remember, we talked about some other interesting things about subsets as well. So here's one. Let's say I look at the numbers from 1 to n, and I want to only look at the subsets that contain number 1. Okay. It has how many subsets containing 1? Well, this would just be 2 to the power of n minus 1. Now, why is that? Let's just look at the correspondence between our subsets and our sequences of zeros and ones. I want to count the subsets that include the number 1. So these will correspond to all the sequences that start with a 1. So I have the same situation as before. I have a sequence of length n. The only difference is that in the first place, I have only one choice because I have to include the number 1, so I cannot start with a 0. I have to start with a 1. I have only one choice for the first letter of my sequence. But then for the next letter, I have two choices. I can put 0 or 1. For the next letter, I can have two choices and so on. So I multiply all of these, and it's just 2 to the power of n minus 1 because I have n minus 1 2s and 1. Okay. But now there was this other problem that we solved using induction, and it was kind of complicated using induction, not very complicated, but a little bit. So let's look at this again. Let's say I want to look at the subsets that have even size. Okay, so I want to see how many subsets of the numbers from 1 to n have an even size. So if I look at all the numbers from 1 to n, I want to say how many subsets does it have that have even size. Okay. Now, because we've done the induction before, we know that the number of subsets of even size and odd size is equal. And we know the sum is 2 to the power of n because the total number of subsets is 2 to the power of n. So this has to be 2 to the power of n minus 1 as well. But I want to prove it in a different way. I want to do it without that inductive proof that we've seen before. Okay. And again, I'm assuming my n is at least 1. So don't care about the case where n is 0. Okay. Because if n is 0, then this is not an integer, and we get into the same problem. Okay. So I have the numbers from 1 to n, and I want to look at all the subsets of these numbers that have an even number of elements in them. Now, again, let's look at what happens when I write these subsets as sequences of zeros and ones. So every subset is a sequence of zeros and ones of length n, right? But what does it mean when I say I want my subset to have even size? It means that the number of ones has to be even, right? Okay, great. So let's say, let's just do a very simple example. Let's say that my n is 6, okay? If my n is 6, then I want to find all the sequences of zeros and ones of length 6 that have either no ones or 2 ones or 4 ones or 6 ones, right? So I can use the addition principle. I can ask how many subsets have, or how many sequences have no ones at all. So how many sequences have no ones? How many sequences have no ones? 1. I can just have the sequence that is all zeros, right? So 1, 2, 3, 4, 5, 6. So the answer here is 1. Then I can ask how many sequences have exactly 2 ones. So if I have 2 ones, I should have 4 zeros, right? So the number of sequences that have 2 ones and 4 zeros is just the number of permutations of 4 zeros and 2 ones, right? So just consider this as a word. Any permutation of this word is one of the sequences that I'm looking at, right? But I know how many permutations this word has, right? This word has just 6 factorial over 4 factorial, 2 factorial permutations. Because again, this is the same idea as before. I'm assuming that all of these letters are different, then they will have 6 factorial permutations. But then because the ones were not different, I've counted every solution 2 factorial times. And because the zeros were not different, I've counted every solution 4 factorial times. So I have to divide. Okay. Now, next, I can ask how many sequences have 4 ones. Okay. Same number, actually. Because if they have 4 ones, then they have 2 zeros. So the number will not change. It's the same as 6 factorial over 4 factorial, 2 factorial. And finally, how many sequences have 6 zeros? 6 ones, sorry. And this is just 1. Right. Because if it's 6 ones, it's just 6 ones, there's 1 left to do this. So my answer is just the sum of these 4 cases. Because whenever I'm doing casework, of course, I'm using the addition principle. So my answer is 1 plus 6 factorial over 4 factorial 2 factorial times 2 plus 1. Okay, now let's extend this to general n. Okay, so in general, I can ask something like this. Let's say that I have sequences of length n. So I can ask how many sequences of length n, of course, I'm talking about binary sequences, have, I want an even number, so let's say 2i ones. Okay. So if I have 2i ones, so I have 2i ones, this means that I have n minus 2i zeros, right? So the number of these sequences would just be n factorial over 2i factorial times n minus 2i factorial. Because if I consider that all of my letters are different, I have n factorial permutations, but 2i of my letters were the same, they were ones. So I have to divide by 2i factorial because I can apply any ordering to them and it will not change the solution. And again, similarly, n minus 2i of my letters were the same, there were zeros. So I have to divide by n minus 2i. Okay, so this is the sequences of length n that have 2i ones. But what was my original problem? My original problem was, what is the number of sequences of length n that have an even number of ones? So I have to sum this up over all I, okay? So I can say that the number of even subsets of 1 to n is actually going to be the sum of n factorial over 2i factorial n minus 2i factorial, where I goes from 0 to n over 2. Okay. Not exactly what I wanted to get, right? So I hoped for a much simpler answer. I mean, we've shown before using induction that the answer is just 2 to the power of n minus 1. But now I got this very complicated answer. Now, the good news is, because we have counted the same thing in 2 different ways, so we've counted the number of even subsets of a set of size n in 2 different ways. Once I counted it using induction in the previous sessions, and I saw that it's 2 to the power of n minus 1. And now I counted it in a different way, and I saw that it's this horrendous formula. So I can be sure that these two are equal. So I just proved a nice formula. I proved that this sum is 2 to the power of n minus 1. Right? So this is an example of what we call double counting again. So suppose that in the exam, I give you this, and I say prove that this is equal to this. One way of proving this is that you just come up with a counting problem. You say, I want to count the number of subsets of a set of size n that have even size. And then you say, I count them in 2 different ways. Maybe I count them using induction, and I show that it's 2 to the power of n minus 1. And then I count them as I did right now, and I show that it's this. And because these two are counting the same thing, they should be equal. Okay. But can we do this without being tortured so much? So can I just get 2 to the power of n minus 1? Yes. It turns out the problem here is that the casework I did was not the greatest casework. I was doing casework on the number of ones that I have in my sequence, right? And that ended up giving me this huge sum because the number of ones is either 0 or 2 or 4 or so on. But let's do something else. Let's just look at our sequence and let's try to use only the multiplication principle. So let's say I have a sequence again of length n. So I have n places. And in each of these places, I can write a 0 or a 1, right? But I want to make sure that the number of ones is even. So let's see what happens. In how many ways can I fill my first element? I can put a 0 or a 1. So I have 2 ways. Right. In how many ways can I fill my second element? Again, 2 ways. I can either put a 0 or a 1, and so on. I can say I have 2 ways for all of these. But let's say that I have filled my first n-1 elements. How many ways do I have to fill the last element? Only 1 way. Because I have to make sure that I have an even number of ones. So when I filled the first n-1 elements, either I have an even number of ones, in which case I have to put a 0 as my last element. Or I have an odd number of ones, in which case I have to put a 1 as my last element. Right? So I have only 1 choice for the last element. And again, I divided this into n steps, and the number of choices that I have at every step is completely independent of the choices I've made in the previous steps. So my total number of ways is just a multiplication of all of these, which is 2 to the power of n-1. And now you see why I didn't give you this solution first, because you would not listen to this one if I gave you this one first. Okay. So we have exactly 2 to the power of n-1 subsets of even size. Of course, I could say the same thing about subsets of odd size. Okay. Great. So now let's continue with this. Suppose that's, well, I started with this idea that I have distinct elements and I care about their order, right? So I was looking at permutations. I was saying when, for example, we were computing P and R, I was saying I have n elements and these elements are all distinct. I think of them as completely different from each other. And I want to put them in a queue and I care about their order. So the next question we solved was what happens if not all of them are distinct, right? But now let's ask what happens if I don't care about the order. Okay. So here's the next question. Let's say that I have n people, so my people are distinct, but I want to choose a team of R people. But I don't care what the order is. I don't want to put them in a queue. So the question is, in how many ways can I choose a team of R people from a set of n people? So in how many ways can I form a team of R people from n people? Okay. Now, another way of thinking about this is that I have a set of size n, and I'm asking how many subsets of size R can I have? Okay. Right. This is exactly the same thing. So how many subsets of n have size R? Okay. Now, we have a notation for this one too. We actually have several different ways of writing it. So people write it like this, CNR or CNR, or just like this, NR. Okay. Now, in this course, I'm just going to call it n choose R. So n choose R is the number of ways of choosing R elements from n elements. But this C usually stands for combination. So how many combinations of R elements can we have of a set of n elements? Okay, so I always also use this notation because I just like it more. So n choose R, but in the textbooks, you will see all of these and they're all the same. Okay, in how many ways can I form a team of R people from n people, or equivalently, how many subsets of the numbers from 1 to n have size R? Actually, we have kind of solved this already, right? In the previous problem, we were solving this for the even values of R, right? So I was asking how many subsets have size 0? How many sequences have no ones? How many subsets have size 2? So how many sequences have 2 ones, and so on. Now, all I'm asking here is how many subsets have size R? So again, I look at the sequences corresponding to these subsets. So I want to write a sequence of zeros and ones of length n. And I want to make sure that I have exactly R1s, because sequences that have R1s correspond to subsets that have R elements. Okay. So this is equivalent to asking how many binary sequences of length n have R1s. Okay, but now this is really easy for us, right? Because I can just look at this number. I can look at the number that has n minus R zeros, and it has R1s. And all I'm asking is how many permutations does this number have? Because the permutations of this number or this word or this sequence, whatever, is exactly the number of binary sequences of length n that have R1s. Okay. But we already know that that's n factorial divided by R factorial n minus R factorial, right? Because again, just assume that all of these letters are different. I have n factorial different permutations, but then my zeros are not different. So I've counted every solution n minus R factorial ways based on how I can permutate my zeros. And my ones are not different. So I've counted every solution R factorial ways based on how I can order the ones. Okay, great. So I could just find the value of C and R, or n choose R. I know that n choose R is now this. And again, all of these are basically the same problem. In how many ways can I form a team of R people from n people, or how many subsets of size R can I take from n elements, or how many binary sequences of length n have R1s? Okay. But can we count the same thing in a different way? So I gave you one way of counting this, but the other way is this. If we go back here, we had this one. We had P and R, which was the number of queues of length R that I can form from n people. So if I have n people, and I want to take R of them and put these R people in some ordered queue, I know in how many ways I can do that, and that's just P and R. Right? But now what I'm saying is that I don't care about the order. So I have n people, I want to take R of them, but I don't care about the order. So let's just do the same thing that I was doing here. Let's take the R people, put them in a queue. That would give me P and R ways of doing it. But now let's just see how many times I have counted every solution. So for every set of R people, I have counted my solution R factorial different ways, because these people could form the queue in R factorial different ways, right? So based on that, I can easily see that this n choose R has to be P of n R divided by R factorial. And I mean, you can also verify that this is exactly what it is, because P of n R was n factorial over n minus R factorial, and you can see that n choose R has another R factorial. Okay. Now, let's continue with this, and let's try to prove some properties of these numbers. So here's the first thing I want you to do. Prove that n choose 1 plus n choose 2, so on to n choose n is equal to 2 to the power of n. Okay. So in this course, I generally don't expect you to do any algebra. If you do it, and if you can solve something algebraically, that's fine, you will get the points. But it's never expected. And I myself am terrible at algebra. So what we want to do here is we want to come up with some sort of a counting problem. And we want to find two different solutions. And yes, subsets, exactly. I want to count, let's say, the number of subsets of a set of size n. Okay, so what is the number of subsets of a set of size n? Well, I've already counted this before, and I know it's 2 to the power of n. So I know that it's my right-hand side. But what is the left-hand side counting? So this first summand here is the number of subsets of size 1. Oh, I've forgotten something. I've forgotten. Okay, sorry. This should be n choose 0 plus that. Okay. Yeah. Prove this. Okay, so on the right side, I have the number of subsets of a set of size n. On the left side, I have the number of subsets of a set of size n that have 0 elements, the number of subsets that have 1 element, the number of subsets that have 2 elements, and so on. So if I just sum these up, it has to be counting all of the subsets. So this is, again, the number of subsets of a set of size n. So I counted the same thing in 2 different ways. So my answers have to be. Okay. Great. So let's do another one. Prove this. Prove n0, n choose 0 minus n choose 1 plus n choose 2 minus n choose 3 plus so on plus minus 1 to the power of n choose n is 0. So more specifically, I want the sum of I from 0 to n minus 1 to the power of I times n choose I. And I want to say this is 0. Okay, how do you want to rearrange them? Yes. So what am I doing here? Again, n choose 0 is the number of subsets of a set of size n that have 0 elements. N choose 1 is the number of subsets of size 1. N choose 2 is the number of subsets of size 2. So what am I doing here? I'm adding the number of subsets of even size, and I'm subtracting the number of subsets of odd size, right? But I know that I have the same number of even and odd subsets. Both of them are 2 to the power of n minus 1. I have already proven that. So this has to be 0. Right. Simplest proof ever, 1 line. I'm not even going to write it. Okay. Now let's make things more interesting. Let's prove this one. Let's say I take n times n choose k, and I say that this is equal to n choose k plus 1 times k. Now, this is one of those examples where you can just write the formula, play with the factorials, get the result. I'm not going to do it. I just don't like doing that. So give me a combinatorial proof. Give me a counting proof for this. And also here, I'm assuming that n is at least k plus 1, of course, because otherwise this doesn't make sense. Oh, I have, sorry. I have another thing here. N times n minus 1 choose k is equal to n choose k plus 1 times, well, am I doing this wrong again, k plus 1? I always have problems with plus 1 and minus 1.
I think you want to choose K people from N people, and then you consider whether someone is in.
Okay, let's make it a little bit more poetic. I want to choose a team of size k plus 1, and I want to choose a captain too. So I have n people. I want to choose a team of size k plus 1, and I want to choose a captain. Okay, so the number of ways is this thing that I have on the right-hand side, because I can divide it into two parts. First, I choose k plus 1 people from my n people, and that's n choose k plus 1. And then I have to choose one of them, designate one of them as the captain, and I can do that in k plus 1 ways. Okay, now how do I get the left-hand side? Well, let's say first I choose the captain. So in how many ways can I choose a captain? N ways. And now I have n minus 1 people remaining, and I have to choose the k other members of the team. So the number of ways of doing that is n minus 1 choose k. So both sides are counting the same thing, so they're equal. Okay. Let's do another one. Prove this. Prove that n choose r is equal to n minus 1 choose r plus n minus 1 choose r minus 1. And again, I'm always assuming that this n is bigger than r, and like n minus 1 is also at least r. So I'm assuming that all of them make sense. You have to prove it only when everything makes sense. Okay. Then n minus 1 is greater than or equal to r. Or another way of making sure that it always makes sense is if I'm choosing r people from n people, and if r is more than n, I say the number of ways is 0. Right? If I just add that convention, then I don't have to constantly write these things.
We're just considering whether the N people is in the team or not.
Yes. So exactly. I have n people on the left, and I want to choose a team of size r. Right? So the number of ways of doing that is n choose r. But I can also do a casework. I can look at the first person, and I can say this person is either in the team or not. So the number of teams is going to be equal to the number of teams that have the first person plus the number of teams that don't have the first person. Now, if I have my first person in the team, from the other n minus 1 people, I have to choose r minus 1 people. So this is the number of teams that have the first person in them. If I don't have the first person in my team, from the remaining n minus 1 people, I have to choose all of the r people. So this is the number of teams that don't have the first person. So n choose r is equal to n minus 1 choose r plus n minus 1 choose r. Okay. Again, you could also give a proof of this using induction and the factorials and everything. I don't want to do that. Okay. Let me see, can I come up with another one? Prove this. Prove that, okay, I'm just going to write it as a sum. N choose I choose j. Okay. I want to say that this is 3 to the power of n, and this is over all I and j that are less than or equal to n. So sum of over all j that is less than or equal to I less than or equal to n. Okay. Again, remember we had a problem in the previous sessions where the answer was 3 to the power of n.
Oh, 3 plus. Yeah. So J is the subset of I.
Yes. So imagine that I have a set of n people, right? These are all of my people. and I want to choose some team, or I want to choose the people who get A in this course, right? And then I want to choose a sub-team. I want to choose the people who will get A+ in this course, right? And the question was, in how many different ways can I do that? Okay. On the one hand, the number of ways is 3 to the power of n, and we have already proven this, but let's just do it using the multiplication principle again really fast. So if I look at each one of my people, there are 3 different places I can put them. I can put them here, or here, or here, right? So basically, I can say that you don't get an A, or you get an A, but you don't get A+, or you get A+, right? So for each one of my n people, I have 3 different choices, and these choices are all independent of each other. So I have 3 to the power of n different ways of dividing people like this. Okay, so I have 3 to the power of n here. How do I get this sum on the other side? Well, I can say, suppose that this n is, of course, the number of the students overall. Let's say the number of students who get A is I, and the number of students who get B is J. So what should I do? If I know that I have exactly I students that get A, and I have exactly J students that get A+, then I first have to choose I students from my n students to get A. And then among these I students, I have to choose J students to get A+. Okay. So this is the number of ways. If I fix the sizes, if I know that this set should have exactly size I and this set should have exactly size J, then the number of ways is n choose I times I choose J, right? But now I was doing a casework. I was saying consider all the possible cases. So I have to consider all the possible values of I and J as long as J is less than or equal to I. And that's exactly what this sum is doing. It's saying sum it over all values of J and I where J is less than. So this is equal to this. But I can also say something else which is very similar. So I can take the same 3 to the power of n, and I can say that this is the sum of I from 0 to n choose I times 2 to the power of I. Right? And you can see why this is the case. Again, you can see it algebraically because the sum of I choose J is 2 to the power of I. We have proven this here. Or you can just think of it like this. Instead of doing a casework on the size of I and the size of J, I'm just going to do a casework on the size of the first set, right? So I'm going to say the number of people who get A in this course is either 0, hopefully not, or 1, or 2, or n. If the number of people who get A is I have n choose I ways of choosing who are the people who are getting A. And then I want a subset of the people who are getting A to get A+. So I have 2 to the power of I subsets. So the total number of ways is n choose I times 2 to the power of I. And of course, I have to sum this over all values. And on the other hand, we've seen that this is again 3 to the power of I. Okay. Now, let's ask a more interesting question. I want you to consider this. I want you to consider this equality, x1 plus, what happened to me? Yeah, okay. So consider x1 plus x2 plus x3 plus x4 is equal to 10. Okay. So I just have this equality. And if I say that my values of x are real numbers or integers, then I will have infinitely many solutions. But I want to ask, how many solutions do I have if all of my xi's have to be natural numbers? So how many solutions does this equality have if all the xi's have to be natural numbers? And remember that for us, natural numbers also include 0. So maybe I can say all the xi's are integers and all the xi's are greater than or equal to 0. So for every I. How many different solutions would this have? Well, let's make the problem easier. Let's imagine that I have only one variable. If I only have one variable, so if I ask you how many solutions are there for x1 equal to 0, that's easy, right? There's only one solution. Or sorry, for x1 is equal to 10, that's also just one solution. You have to set x1 to 10. Now let's do it like this. Let's say x1 plus x2 is equal to 10. How many solutions do I have now? Well, I can do a casework on x1. I can say x1 is 0 or 1 or 2, so on. And whatever value I choose for x1, I will have a unique value for x2. So I have 10 solutions. Or 11 solutions, 11. But what if I say x1 plus x2 plus x3 is equal to 10? You see, suddenly it becomes much harder to do the casework. Because now I have to do a casework on x1, and then inside that, I have to do another casework on x2. And basically, we're getting to a point where I'm just writing down all the solutions and counting them one by one, which is too hard, right? So I want to count this in a nicer way. How do I count this in a nicer way? So try to somehow change this problem, reduce this problem to a problem that we have already seen. So we know how to solve problems that involve choosing something or counting the number of permutations, right? But now I have a problem that doesn't look like that. I have to somehow change it so that it looks like that. Okay. So here's one interesting thing. Let's say that I have 10 balls. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Oh. And let's say that I have 2 balls. So I have, let's say, a ball here, and I have another ball here, right? So I can count the number of balls that are before the first ball, that's 3. And then I can count the number of balls that are between the 2 balls, that's 1, 2, 3, 4, 5. And the number of balls that are after the last ball. And these will give me 3 numbers whose sum is equal to 10, right? So in this case, I get 3 plus 5 plus 2. So I can take any solution to this equation, and I can turn it into a permutation of 10 balls and 2 balls, right? Because if I give you a solution, if I give you, for example, let's say 1 plus 2 plus 7 is 10, right? So you can just say I put 1 ball, and then I put 1 ball, then I put 2 balls, then I put a ball, and then I put 7 balls. Okay. So I can translate any solution of this equation to some permutation of 10 balls and 2 balls. And I can do the same thing in reverse. So there is a one-to-one correspondence. Every solution corresponds to exactly 1 permutation of balls and balls, and every permutation corresponds to exactly 1 solution. So the number of solutions is equal to the number of permutations of 10 balls and 2 balls. And okay, how many permutations do we have? We've solved this before, right? So I have 12 objects, so I have 12 factorial permutations. But then 10 of my objects, the balls are all the same. I don't distinguish between them. So I have to divide by 10 factorial, because all the orderings of these balls will give me the same solution. And then these 2 balls are also indistinguishable to me. So I have to divide by another 2 factorial, because any ordering of the balls will not change my solution. So the number of permutations here is 12 factorial over 10 factorial, 2 factorial. And so the number of solutions to that equation, what? Oh, so I have two vols. I have two types of letters. Imagine one letter is the ball, one letter is the vol. Okay, so I have two vols and I have 10 vols. So it's 12 factorial over 10 factorial 2 factorial. Now, let's go back to my original problem where I had 4 variables instead of 3. So the only difference is that now I have one extra vol, right? So I will have 3 vols and still 10 vols. So the number of solutions here would be 13 factorial over 10 factorial 3 factorial. Okay, so I have 13 objects. 3 of them are vols, I don't distinguish them. 10 of them are balls, and I don't distinguish between the balls. Okay, so in general, if I have something like this, if I have x1 plus x2, so on, to xr is equal to n, and all of my xi's have to be greater than or equal to 0, then I need r minus 1 vols, right? And I have n vols. So I have n plus r minus 1 different elements. So distinct factorial divided by, and then n of my items are the same. I have n vols, so n factorial, and r minus 1 of the other items, which are the vols, are also the same. So divided by 1. Okay. But there is another way to get the same solution. And this actually shows you some interesting point here. So here's the thing. I want to count the number of permutations of a number of balls and a number of balls. In this case, I had 10 balls and 2 balls, right? So we've seen one way of counting this, but here's another way. I can say, well, I have 12 places, and in each one of these places, I have to put either a ball or a ball, right? And I know that among these 12 places, I have to put balls in 2 of them. So let's do that. Let's first choose 2 of the 12 places. And in how many ways can I do that? 12 choose 2. And let's put balls there. Now I have 10 remaining places. Let's put balls in all of them. And there's only one way. If I have 10 places and I have to fill all of them with balls, there's only one way. So the number of ways is 12 choose 2, which is incidentally exactly the same thing, right? 12 factorial over 10 factorial 2 factorial. And one last thing, this is a very simple last theorem that I want you to prove. Prove that n choose r is equal to n choose n minus r. Okay. So, and again, I have that r is less than or equal to n. Now, on the left side, I'm saying that I want to choose a team of r people from a class of n people, right? So the number of ways of doing that is n choose r. But if I want to choose a team of r people, I can instead choose n minus r people and kick them out, right? So the number of ways to choose n minus r people and kick them out has to be equal to the number of ways to choose r people. So n choose r is equal to n choose n minus r. You can also just write the formula. This is like n factorial over r factorial n minus r factorial. This is n factorial over n minus r factorial, and of course they're equal.